Good morning, everybody. My name is Stuart Halloway. I work at Cognitect, and we're going to be talking about core.async, which is, well, let's just jump in and take a look. So I want to start with a problem statement. And like a lot of good problem statements, this is a problem statement that requires you to solve more than one problem at a time. I mean, one of the challenges in software development, especially when you're taking an incremental approach, is you don't necessarily get the entire surface area of the problem out in front of you. And you know, this is a danger, maybe particularly with agile methods, because you bite off little bites, and then after a while you look back and go, a comprehensive approach to this would have come to a significantly different answer. So a couple of things. The first one is that objects are not really good for modeling. And in particular, they make terrible machines, because objects are like marionettes. And anybody can reach in and touch them at any time. And so it's very difficult to control systems as they get larger when they're made out of objects. So it would be typical and appropriate, circa 2015, for me to then say, well, of course, functional programming is the solution if objects are the problem. But functional programming doesn't make great machines either. Right? There's all kinds of wildness when machines actually have to be stateful and have to interact with other things. That's really a topic that is either not covered in functional programming or is covered with complexity and the M word and things like that. So they're not great machines either. Also, as you build systems, you discover that having things directly connected to other things becomes a problem. Right? If you've ever said the word dependency hairball or the word spaghetti code or anything like that, a lot of that comes from having object or data structure A depend on B, which depends on C, and all those things have to be wired together and connected. Then we get to a more specific but easily perceivable problem, particularly in UI programming, in environments where we don't have great threads or great control of threads, and that's callback hell. Right? You want to do something, but you don't want to do it right now, and you don't have threads, or you want to respond to something, and the only way to build things that way in certain approaches is callbacks. Now, the solution, sort of, to all four of these first problems could be queues. So we could just say, well, if we use queues to separate our machines, right, they're little conveyor belts between our machines, then the machines don't have to know about each other anymore. So there's great indirection, right? The machines only have to know, some kind of package comes off a queue and I do something with it and I put it on another queue. So that would be pretty cool. So we're not, chaining together objects or chaining together functions anymore, and we're not directly connected. The problem is that the implementations of queues that we have are pretty coupled to threads. In particular, a lot of people write code that runs on the JVM, and the Java util concurrent queues, as awesome as they are, block real threads. And it's trendy, and for good reason, not to consume real threads. So we'd like to have some way to do things that doesn't involve consuming threads. And so threads kind of suck even whether they're good or bad. Right? When threads are good, they're expensive and you don't want to use them. And when threads are bad or non-existent, you don't have a choice. You can't use them. So these are the problems. And core.async is a compelling solution to this set of problems. It's not a solution to all problems. It's not a floor wax and a dessert topping. But it is a dessert topping that solves all these problems. So what's the opportunity here? We want to have a first-class conveyance that's like queues. And a lot of the things I'm going to say today about how you would design or build systems, you could easily lift from probably hundreds of different conversations on the web and research and academia and practice and production that are all about queues. But they can't be queues for the reasons we just talked about. We want to have a model for processes. So these are the actual machines that consume things from queues and put things on other queues. So throughout the rest of this talk, the granularity of process is going to be, I'm going to use that word to talk about something inside of an operating system process. So we're going to compose an OS level process out of lots of smaller processes. And we could pick a different word for that, but I'm not going to, because that's what the academic literature uses. And so I'm going to maintain faithfulness to that at the cost of you having to sort of keep in your mind that when we're talking about processes here, we're talking about an independent scope of control, but we're talking about something that's going to be smaller than an operating system process, and you're going to have a lot of them in an operating system process. This solution is not going to be a brave new world where you don't get to use your existing tools and libraries. So in order for this to be really great, it needs to be integrated with platforms that you might already be running on. And the two platforms we're going to talk about are the JVM and the browser as a platform. And by putting all these things together, we're going to be able to build systems out of robust subsystems. And this is, the classic problem of spaghetti code, that you don't feel like you have a robust system, right? You reach in and you tweak something over here, and what happens? Right? Something falls down, but it's failure at a distance. That's the worst thing in software, and especially when it's combined with intermittent, right? You do something over here, and then sometimes over here something catches on fire. And in my experience, that sometimes is not during your shakedown tests, and it is in front of your biggest customer. So we want to be able to build robust subsystems. So that's what we're going to do. Now, it turns out that lying on the shelf for decades now, there has been a technology that really elegantly solves these problems, and it's called communicating sequential processes. And what CSPs provide are an abstraction for processes, right? A thing that represents an independent flow of control. An abstraction for conveyance. You could say queues, but the actual term in the literature is channels. And those things together form a new kind of concurrency primitive that you may not be used to. It's a coordination primitive that says, if I'm going to put something on a channel, then I am going to block or pause or stall, and we'll talk about the semantics there, until someone else can take it off. So that's a handoff. It creates a simultaneity point between two different processes. In order for me to produce something, you have to be ready to consume it. And then, using these tools, we're going to be able to write programs that, in their aggregate effect, are complex and asynchronous, but locally we can reason about, because the individual machines are sequential. Right? There's a machine that says, take something off of this queue and turn this crank and put something on these two queues, except on Tuesdays, take something off of this queue and turn a different crank and put something on this other queue. But all of that logic is going to be linear, and it's going to read as if it was all going to run sequentially. So this is actually a really great name, communicating sequential processes. It's exactly what it does. Right? You compose your system out of lots of little sequential things, which are easy to write, easy to test, easy to reason about. Now, we're going to add a couple of things on top of that. One of them is multi-reader and writer. So if you're used to using queues as an abstraction, you may not be accustomed to having the ability to say, I want to do a blocking read-write on 4 different queues operation. So I want to either take something off this queue, or write something to this queue, or write something to that queue, or write something to that queue. On the other hand, if you've written a lot of OS-level code, you may be very familiar with doing that kind of thing. If you're a Unix programmer or a Linux programmer, that's called select. Right? It's something that lets you try to do multiple things at once and let one of them win. If you are a Windows programmer, that's called co-wait for multiple handles EX. And I think that tells you everything you want to know about Linux and Windows, kind of in a nutshell. And then we also want to have buffering, so that coordination point, coherent sequential logic, that's going to be great when it is, but every once in a while, when you start to think about policies between these subsystems, you're going to ask questions like, well, what if this guy is putting things on to the conveyor belt faster than she can take them off? What do we want to have happen in that system? And the coordination point says, we're just going to lockstep everybody to the slowest and most broken subsystem, which sometimes is what you want. Right? Sometimes subsystems need to chain together and say, you know what, if all 5 of these things don't trigger, then we don't want to have done anything. So that's totally appropriate. Other times, you're going to want different policies. So there's an ability to say that these channels are going to have buffers in them. Now, if you followed everything I've said, we're kind of done now. And we can actually just sort of hang out or go to the bar or whatever. However, the conference organizers have explained to me that we want to stagger going into lunch. So I've been instructed to run long by 5 minutes. So I just want you to know that in advance when we go 5 minutes past the end time, that I'm doing it on purpose. Not just being mean, or I'm being even meaner because I'm keeping you from food. But in order to do that, I'm going to go ahead and continue. This is actually the last slide, but I'll go ahead and continue the talk for a little bit longer. So, what are we going to do? So this is the sort of canonic picture of what it's like to build a system like this. And the thing that's great about this is you write that little green box, and it's colored green because it's relaxing and peaceful. And it's relaxing and peaceful because you do sequential things. You say, go and grab something off of this channel, go and grab something off of that channel, and then put something on that channel, and then put something on that channel. And your program is built out of these little machines that are easy to reason about. There are 2, in the actual implementation we're going to talk about of CSP, core.async, there are 2 first-class process abstractions. One of them is called thread. Thread is available on platforms that have real threads, and it uses a real thread to implement the process. Go is available places that do not have threads, And Go rewrites your program internally to allow you to write a sequential code, sequential code in this block, and it will schedule pieces of it onto whatever is available on your platform. So if you are running on a platform with threads, Go will use a thread pool. If you are running on a platform without threads, it will actually do, once and for all and in one place, magic callback hell behind the scenes to schedule all this, and then you write all of your code, forgetting that that stuff exists. So that's your processes. You've got two kinds of processes. And then there are channel operations, and the channels are really simple, right? You can put things onto the channels, and you can take things off of the channels. And the APIs are different depending on where you're coming from. If you're working in a Go block, you can say put something on a channel, the single bang put and take operations. So the arrow bang, in bang, and out bang, if you will. Those are, I'm running inside of a Go block, and I want to put something on a channel. Then there are the threaded versions, which are the double bang versions. I'm consuming a thread, and so I want to put something on the channel or take it off. Those will block. Right? We talked earlier about these channels act as a coordination primitive. Those will block. Well, what do you suppose the Go ones do? They can't block. Right? They don't own a thread. So we use a different word to talk about essentially getting the same semantic from a programmer's perspective. They park. And what that means is that the execution is suspended and the state is remembered and it's kept in a table, and then when it can execute again, it gets scheduled again on a thread pool or whatever the underlying substrate that you're working on is. And then finally, and we'll talk about this one early because it's important when you actually go to write programs, there's also the ability to do the English word put bang and take bang, and that's for integration with external things. Right? So the minute you start trying to use this in a system, you're going to have a system like a web browser that's creating events. You're going to have a front door there that events come in, and you're going to have one loop that says, whenever I get an event, put it on this channel. And now you're done. You never see callbacks again. So let's take a look at a set of examples that demonstrate this in the browser. And these are going to be single operation examples. So I haven't shown you how to do multiple things at once yet. I've only shown you how to put things on a channel and take things off a channel. But even with this, we can do some pretty useful things. The examples, the slides, the link at the bottom takes you to all these examples. The examples are all on GitHub. And in the case of the first couple of examples we're doing, these examples also have a webinar that goes with them that David Nolan, who wrote a lot of the code behind this, presents this stuff. He's a very smart guy, and so if you're at the end of this, you're like, wow, that was so cool, I'd like to do it again, but with a smarter person, then you could go and watch the webinar. Now, it occurs to me that I've done something a little stealthy here, which I started showing you closure code. And it's probably important. How many people can read closure code like nobody's business? How many people are nowhere close to reading closure code? That's good. That's courageous. How many people don't raise your hand when you ask questions in conference talks? OK, so now we know. So I'm going to teach you how to read Clojure programs. Fortuitously, Clojure is one of the easiest languages to learn at the basic level. It's a little bit like Go. Right? It's really easy to learn the rules, but then there's a lot of things you can do with it. So here are the rules. Here's a hello world program in Clojure. That is the program. Right? So a Clojure evaluation takes a piece of data and reads it and evaluates it. And every kind of data has evaluation rules. And almost all kinds of data, the evaluation rule is just return the thing. So for strings, the evaluation rule is return the string. For numbers, the evaluation rule is return the number. For vectors, the evaluation rule is return the vector, and so on and so forth. So it's really quite an easy language. When you look at a Clojure program, it looks almost like, if you squinted at it, like JSON with a few less strings. So here is a Clojure program that represents a piece of data. It's a map that contains information about an address book, and then it's a submap, and so on and so forth. And this is another example of a program whose evaluation semantics are return the thing. Right? There's very little do the thing. There's almost always just return the thing in Clojure. And just to round that out, strings are in double quotes. Character litters are preceded by a backslash. Integers and floating point numbers can be written in machine precision or arbitrary precision. The capital N and capital M suffixes have to do with arbitrary precision. Booleans are true and false. There's a nil. And there are two symbol types, or symbolic types. There's a symbol type that is usually used to name programmatic constructs. So to name methods and classes and packages and things like that. And those symbols are unadorned. They look just like words, or just like punctuation characters, so plus. And then there are symbols that evaluate to themselves. and do not refer to programmatic constructs. And those look just like symbols, but are preceded by a colon, and they're called keywords. On top of these, there are 4 aggregates. There's a list, which is in rounded parens and represents something that's navigated sequentially from the front. There's a vector, which is in square braces and represents something that can be sequentially or randomly accessed positionally. There's a map, which represents an associative collection. So here we have a map from the keyword A to the number 100 and the keyword B to the value 90. And then we ran out of punctuation types. We thought about angle brackets for sets, but then we figured people would run screaming. So sets actually take advantage of the pound prefix to say, interpret this next character to mean something different. So that's a set containing the keywords A and B. Now, the cool thing is, you now know closure. That was it. That wasn't so bad. Let me tell you about a couple of things that you didn't see. There aren't any semicolons, and there also aren't any commas. You can put commas in if you want. They're white space, so knock yourself out, putting commas between things in vectors for the first couple of weeks. And then after you go from closure back to JavaScript, you're just going to be screaming at JavaScript when it's like wanting commas everywhere. Like, why are you doing this to me? So the only other thing you need to know to run closure programs is to know that lists are special. The evaluation rule for a list, and actually for symbol, are different. The evaluation rule for a list is take the first thing in the list and treat that as some operation to perform and treat the other things as its arguments. And then the evaluation rule for symbols is look up the code associated with this or the data associated with this. So this is actually a program that says add 2 plus 2, right? When Closure encounters this piece of data, it says, oh, it's a list, something to do. The first item in the list is plus. That is a symbol that happens to point to a function that does things you might expect. And so there's a program. And all programs just look like this. And so now the only other thing you need to know to be an advanced Closure programmer is the willingness to sit down and learn, at first 25 and then eventually 150 different other things that can go where plus goes. I'll show you one more just to show you how it gets richer. So here's the function defining function. Def_in defines a new function. It's a function itself, right? Because everything is made out of the same underlying stuff. And it takes an argument that is the name of the new function to be defined. It takes an argument that is the documentation string for the function. It takes an argument defining argument, right? So here the vector containing your name says that this function greet takes one argument. And then it has the body of the function, which does whatever. And I'll just introduce one more little function here, stir, which just sticks a bunch of stuff together in their string representations. But notice that this is still all data. All right, so now you know enough that we can go. I don't really want to focus on closure, because that's not the important thing here. But I wanted you to see just enough that when we read programs, we can get past that immediate, like, oh my God, there's parentheses, or oh my God, there's not semicolons or commas, whichever way you see that. So let's go and look at a really exciting web application. So I'm going to show you a web application that does some not very interesting things, and then we're going to gradually make them more interesting. And I want you to think about how you would implement these in JavaScript. So this first example is a button that I can click, and when I click it, I'm told got to click, and when I click it again, nothing happens. Right? So I want to emphasize there, that was a stateful interaction. Right? It's not a stateless system, because the first time I did something, it did something, and the second time I did something, it's not doing anything anymore. Now look at example 2. I click this. Oh, this one's different. I can click it again. Oh, but that's also a stateful interaction. Right? But it's a stateful interaction with more than one transition. Right? It starts from I'm willing to accept 2 clicks, and then it moves to I'm willing to accept 1 click, and then it moves to I'm done. Now I'm going to look at a system that has 2 different pieces, button A and button B. So I'm waiting for a click from button A. What happens if I click button B? Nothing. But if I click button A, I have now unlocked button B. Actually, it went ahead and consumed the click from button B earlier. That's interesting. And then we'll look at waiting for a click. Now this one's stuck. This particular little program, when we go look at the source code, it actually rendered some stuff on the screen, and then it tried to put a value on another channel. But we don't have any, you remember that's a coordination primitive. The interesting thing about this when we look at the code is we don't care that one of these Go blocks gets stuck. That's fine, right? You can make these things, they're cheap. You can throw them around if you have one that gets stuck. If it gets stuck and all of the things it could ever reach on the outbound side eventually become unreachable, it gets garbage collected. It's just a thing, right? So you can make these things in a really casual way. And then we'll click this guy, and we actually took the value from the channel in this example. So now let's go look at the code. So let's see here. That's really big. I'm going to make it a little smaller. I'm going to try to make it a little smaller. And I apologize, I want to make it small enough to see. So the first thing I'm going to show you, well, this is the first example, right? So this is a function called example1. It says, I want to make a channel that gets the clicks. So it calls a helper function that we'll look at in a second. And this is that thing that does that boundary logic between the outside world, outside async, and your world, right? Because we know that out in the world of JavaScript, where do these clicks come from? Right? They come in as events. So this little events to channel helper function goes out and grabs the DOM element whose name is example1 button and grabs click events and then puts them on a channel. And then we're going to create a show function whose job it is to write things into a div. Right? Again, this is not super exciting. This is JavaScript programming, so I'm not going to focus on it. And then here's the little program. Go, show the initial thing, pull something off the channel showing that the button was clicked, and then show what we got. And we'll just go and look at events to channel up at the top here. Right, events to channel just says events/listen. So this is actually calling, I guess it's Google's library, goog.events. So that's Google's JavaScript library. But this could just as easily be jQuery or whatever. Right? This is that's Clojure's interop form for calling out to JavaScript. So this happens to use Google's library, but you could use whatever you liked for that kind of stuff. And then it says, and here's the key thing. Whenever I get an event, this is the one callback handler in my whole world, right? Whenever I get an event, I'm just going to turn around and put it on this channel. Now, the rest of my logic is sequential. And so what does it take to implement a stateful thing? Well, here's that one that goes through two states. Right? This is what I mean when I'm talking about coherent sequential logic. Right, I'm going to say, wait for a click, grab the click, announce that I got the click, wait for another click, grab it, and say done. How would you implement this if we're using callbacks? Right, what's that? You start to build a state machine. And the thing is that the callback thing actually doesn't start to get scary when you're only responding to one thing. It doesn't get too bad yet. It starts to get worse when you start to say things like, I want to interact with more than one thing. So now I've got two different things. I'm going to respond to button A, and I'm going to respond to button B. So grab the click off of A, do some stuff. Grab the click off of B, and do stuff. And as you start to multiply this out, and you start to do things like, and we'll see this in a minute, you start to do things like, I want to have 3 different things that can trigger this action. Right? This mouse event can trigger this action, or this scripting event can trigger this action, or this keyboard stroke can trigger this action. Then you start to sort of get that, what people call callback hell, going in your JavaScript. And then here's the one that's stuck. So this is a program that says, I'm going to wait for a click that comes in via an event, and then I'm going to try to put the date onto a channel. And I'll never see this line of code. And if this channel gets garbage collected, right, if this channel that I'm trying to write to, C0, gets garbage collected, then this whole Go block can get garbage collected. So you can just fire these things up and not worry about it. And then here's one that actually gets past that. This one actually starts 2 separate programs. And this also starts to get to the difficulty of modeling this when you can't start sequential processes. This starts a sequential process that does one job, and then it immediately starts another sequential process that does another job. And I'll show one more example of that, a different program here. So this is a program that shows essentially threads for JavaScript. I want to have a thread that throws the word red on a channel. So this loops forever, sleeping for a quarter of a second and throwing red on a channel. And then I want to have a separate little program that I write that throws blue on a channel. And notice that blue happens only 1/4 as often because the sleep is longer. And then I have a separate program that throws green on the channel, which only happens once every 2 seconds, so that's going to come in even less frequently. And so what I've written, the way I've composed this program is I wrote a little tiny program that deals with red. I wrote a little tiny program that deals with blue. I wrote a little tiny program that deals with green. And then there's a 4th program that's not actually, the source code's not shown here, that does the rendering. And if we go and look at that program, if I can remember where it is. So you get when you open too many. Exploring Clojure, CLJS. So that program that does the rendering does this, right? It loops forever. It initially puts the word ready on the screen, and then it takes the value off the channel and renders it by calling setHTML. So again, I've written my program as a set of infinite loops that do different jobs. And then I just walk away and forget about it. I just start the different machines running and walk away. All right. Now, one of the things that happens when you start writing programs like this is that you essentially want to do multiplexing and demultiplexing of various kinds, right? So you have 2 or 3 different kinds of inputs coming from the outside world that you want to have all trigger the same action. You want to route 2 different things to the same channel. Or you have something that you want to trigger in different things. So some input comes in and you want to route that input to a bunch of different places. There is no rocket science to the next 5 slides. This is the easy, like, take a stretch break and tune out, because there's nothing going on here. There's just a set of functions that do that, right, that do multiplexing and demultiplexing. So there's one called pipe. If you find yourself with a channel in one hand and a channel in the other hand and they're not already connected because somebody else made them, then you just call pipe and they're now connected. The stuff that comes in on that one, appears on the other one. Or you can call merge. So you have 2 different sources of input. Let's say channel 1 represents mouse events that you want to have do something, and channel 2 represents keyboard events that you want to have do the same thing. Then you can merge them onto another channel with merge. Or turning things around, you can split a channel using a predicate. So this says, I'm going to take a channel, and things that match P are going to go to this one channel, and things that don't match P are going to go to a different channel. But the other thing you start to get into here is that sometimes you're building a user interface that you don't know what's going to be wired up until you get started. Right? So everything I just said is like statically putting all the conveyor belts in place when your application starts. But imagine that you're building a game that's one of those resource economic games where you gradually, you farm the land and you get metal and you build armor and then you can build phalanxes and all that kind of stuff. All those new things that come into the game don't exist at the beginning. And each one of those independent entities needs its own process and needs its own input and output, or needs to respond, and it may need to respond to things that other people are already responding to. So basically you need to have a stateful ability to say, I want to take this channel and distribute it out to other channels. And so there's a thing called a mult. And what a mult does is it creates that distributor. And then anybody who wants to can tap it. And the difference between this and the stuff we saw before in terms of splitting things out is now you can do it dynamically at runtime. You can say, when I start my program, all the soldier tokens in the game want to find out about this kind of thing, but they don't all exist yet. So every time I make a new soldier process, then that soldier will tap into an existing mult. And of course, for completeness, there's mix, which does that in the other direction. So you can dynamically mix in things. And then there's full-on publish and subscribe. So you can say, I want to subscribe by topics. And the topics are some function of the data that gets put on the channel. Right, so you put data on the channel, and you have a function that can say, looking at this data, this person's interested in that part, and this person's interested in that part. And so you can distribute things out that way. All right, so that's all pretty easy. Now for the most subtle part, and that's doing multiple operations at once. What happens when you have one process, and we've already saw that our processes talked to more than one channel, but they didn't talk to more than one channel simultaneously. Right? They said, I'm going to get something off of this channel, and then think, and then put something on that channel. What happens when you have a process that you want to say, you know what? I want to get something off of this channel or that channel. And then I'm going to make a decision based on what happens. And so everything that starts with alt, which stands for alternative, lets you do this kind of thing. It lets you wait on multiple operations at once, as many as you want. It's very similar to Unix's select, as I said before. And I'll show you the syntax first in its full glory, which will be a little blinding, and then we'll show some examples that make it a little more straightforward. So here is an alt that's trying to do 4 different things. It's trying to take from channel C and call foo. It's trying to take from channel T and call foo. So that bracket around C and T says, either one of these channels I want to do the same thing with. Then it's saying I want to take from channel X and return just the value that I got back. Or I want to write to the out channel val. So this is an extremely convoluted example, right? This is something that's trying to talk to 4 different channels at once. It's fairly unusual that you get, 2 is incredibly useful and it tapers off after that in practical applications. But this just shows all the syntax in one slide. And then finally, in this particular case, this alt will terminate immediately even if none of the channels are available with the value 42. A lot of times you'll use alt without a default. Right? Again, you want to make an infinite loop. You want to make something that's just, I'm going to wait for one of these things to be available and then do them. And so now we'll look at the multi-operation examples. These are going back to the same set of examples we were looking at before. I will reload that so it can rest because my laptop's getting tired. All right, so here is I click on this button and then it will start tracking the mouse and reporting where the mouse is. Oh, sorry. I did 70% of what I was supposed to do. Let's do the rest of it. And now we are all excitingly together on the same web page. So I'm going to click on Go, and now this is tracking the mouse and reporting that, and then stop. Right? So this is a stateful thing. Right? There's stateful operations here. The button changes state. It changes from being a Go button to a stop button, and the behavior that happens in the background. And then we'll look at the next one, which I'm not sure how this one's different. And this one requires the button to be clicked 10 times. So this is stateful, and it proceeds through 10 clicks, after which it's done. The button doesn't do anything anymore. And then these last two examples, this one cycles through a list of animal names. If you ever play that game with your kids where you have to name an animal, and then they have to name the animal starting with the last letter of that name. It's like I say aardvark, and then you have to say kangaroo, and haha, it caught you because O's hard. But you say orangutan, and on we go. But this actually just goes through the list in alphabetical order. And then this last example does the same thing as the first one, but it puts lifecycle around it. The entire subsystem is only enabled once you click on Start. Then you can work through, and then you can stop. So if we go out and look at these, they are somewhat more substantial. So now we are responding to a couple of different buttons. And we are responding to clicks and to mouse messages. And this setbang is just interop to talk directly to the DOM. So that dash inner HTML is the inner HTML of a DOM element. And then the important piece here is that we're alting on the mouse and the clicks channel. Right? The mouse channel represents a mouse move. So if that comes in, what do I want to do? I want to keep displaying updates. But if someone clicked again, then we're done. So after this alt, we can go back and say which thing happened. Did the channel that come back, was it clicks or was it the other one? If it's clicks, we're done. Otherwise, we're going to show the position of the mouse and loop. So this is an example of a not infinite loop anymore, because it's looking at two different channels, and one of the channels gives it a way to terminate. Right? If somebody clicks on this, then we're done with this little subprogram. And they just get more substantial. I'll go all the way to the most complex one. Woohoo. So here we have three buttons we want to look at. The start stop button, the previous button, and the next button. And we want to watch a channel on each of those. So we'll stick a channel on the start stop button, a channel on the previous button, a channel on the next button. And then we will keep track of our animal's data structure. And then it's a much more complicated program. It's like 25 lines of code. So we're going to wait for somebody to click the start stop button. Then once they do, we're going to turn that into a stop button. And then eventually, and this is the meat of it, we're going to say, I want to alt on actions or start stop. And if the actions channel has something, and notice that actions is actually merging three different things, right? We're looking at three different things on the same channel. And then this could actually be made, like if I were doing this in a real program, this could be made a little bit smaller and tighter, like the data structure manipulation of handling previous and next and doing the math of am I at the end and so forth. The purpose of this is to show you, not necessarily in this case the most idiomatic code, but to show you that you can always write your program out of a bunch of small, wholly linear pieces, right? Do X, I mean, this is fantastic. You sit down and you have your requirement for how a feature is going to work. Well, it needs to start, has some life cycle, then it needs to do this for a while, and then it needs to do that, and it needs to end. All your programs have exactly that shape. And then the last example I'll show for that is actually the canonic example that people use, which is search with SLA. So I should back up now and mention that communicating sequential processes is realized in Clojure as a library called core.async. And that's a library that that's what we're talking about here. That's a library that you can run on the JVM, or you can run via ClojureScript in the browser. But the other really popular language that's out there right now that also does this is Go. And it's probably not a coincidence, right? The signature feature of Go is, of course, the Go routine. And if you watch the introductory Go talk, which is linked there, you'll see this example written in Go syntax. This is also nice if you are super excited about async, but you're not that into Clojure syntax. Then you can go and look at a lot of the stuff I said today is also realized in a more traditional algol-like syntax in Go. But what this thing is doing is it's a Google-based example. So Google's obviously obsessed with search and response time. And so the mission statement here is, I want to, as a user is typing in the browser, I want to search for related web content, I want to search for related image content, and I want to search for related video content. And for each one of those sub-searches, I want to search two different servers in case one of them's down. Right? Maybe web 1 is down and web 2 is good. And I want to show all three of those kinds of content if they're available within 80 milliseconds. And if not, this is a type ahead feature. Right? So if somebody's typing and I can't get the answer in 80 milliseconds, then I'm done. And so what this lets you do is, I'm going to start a program. This first Go loop is a program that says, go off and asynchronously search against two different web servers and give me back whichever one comes back fastest. The second one says, I'm going to go search two image servers, give me back whichever one comes back fastest. The third one is going to say, I'm going to go back and search two video servers, give me whatever comes back fastest. And then I'm going to also, when I do my alt, the alt is going to consider the possibility of a timeout. So this T is one of the things that I'm alting on. And so I can get out of here early if a timeout happens. So this allows you to orthogonally compose a timeout policy on top of a bunch of other things. Imagine writing this without threads using callbacks. Right? I'm going to start this thing over here, and that thing over there, and that thing over there, and I'm going to keep state somewhere. Don't know exactly how to do that. This turns a hard problem into a trivial problem. While we were here, I should mention that there are a couple of interesting differences between Clojure's implementation of CSP and Go's implementation. Go implements CSP as a language feature. So the operators in Go are statements. Right? They're actually part of the language. Clojure implements them as expressions in a library, which means that Clojure's feature here, you can metaprogram against it. Right? You can reflect against it its data. You can manipulate it in all the same ways that you know and love about working in a Lisp language if you work in a Lisp language. Those things are available here. Also not super important to me, but alt in Clojure supports priority. So you can say, I want to alt on these different channels, but if they both come in nigh simultaneously, I can prioritize taking this one over that one. So those slides are slides that I wrote, I don't know, whenever we released core.async. Many eons ago. And for today, the Philly ETE organizers challenged me to take it to a more advanced level and to say, you know what, okay, let's talk about how to actually build things. Like you've seen some small toy examples. Talk about your thought process when you're building systems this way. And so I want to talk about what it's actually like to work with this. And I want to start by saying that when we released core.async, I was not able to use it initially. So I really have about the best job in the world, right? I work on Clojure, I work on core.async, and I work on Datomic. But Datomic is a commercial effort that lots of people depend on. And so I was in the unusual position of being at the company that's behind core.async, but Datomic doesn't use core.async because all the things that we would have used core.async for in Datomic were written before we had it. And we're not just going to go wantonly. We're not that kind of developers, right? We're not going to say, well, we have a better way to do it now. We're going to take this code that's not broken, and we're going to take a 2-month hiatus and rewrite it to use this new cool thing because it's shiny. So we launched core.async, and everybody in the whole Clojure ecosystem gets to play with it, except the core Clojure team, people who happen to also be working on Datomic. So I have not gotten to use this very much until we started some other initiatives that are coming out later this year that were greenfield for me. And so being able to go back, and I should say, having written all of Datomic using threads and Java queues, I'm keenly aware of what I wish I had when I was doing those pieces. So this is my kind of summary list, and we can probably take a pretty substantial amount of time talking about this slide, because this really represents my view of how the world changes. And the interesting thing about it is that it really changes whether you're an object-oriented programmer coming to it or whether you're a closure programmer. So if I imagine the way people build programs, and I'm going to talk about it in terms of closure, that's this without async column. So I'm building a system. How do I sort of pull pieces together? Well, the arguments to my non-trivial entry points represent substantial other pieces of the system. And I'm going to call those active objects. If I were in an object-oriented language, they would be horrific, mutable, update in place objects. But even in closure, people would idiomatically say, I'm going to pass around a thing that's on top of an atom, or that's on top of a software transactional memory reference. So it's got sound concurrency fundamentals baked in, but still represents passing around these active objects around the system. With async, arguments are maps. They're plain old maps. They're like the stuff that Jessica was showing in her talk. It's just maps, data everywhere. The primary abstraction mechanism that people like to use in closure is protocols. If you come from an OO background, think interfaces, right? Interface inheritance, that kind of thing. With async, I never talk to anything else directly. Right? I'm always going to be indirected from the other subsystems by a channel boundary, which means there's no protocols, right? The protocol for channels we already saw. It's put and take. So all the actual semantic communication is whatever you put in maps. Invocation between subsystems, people typically build programs that all the subsystems talk to each other by making method calls. That's the OO way. That's how you get spaghetti code, right? Everything depends on everything else in subtle ways. Here, nobody ever talks to anybody. Everybody just puts things on channels. Queues are kind of an afterthought in most programs, right? You know, you put them in for pipelining, or maybe you put them in after the fact to create some isolation when you've been cognizant of specific pain points. With async, they're the primary boundary, right? They're where things stop. I mean, it's not interfaces, right? All the places where you'd have put interfaces in your UML diagram, you're now going to put channels. And then orchestration gets really interesting. So orchestration of a typical Java app is you pass a bunch of objects to a bunch of constructors to build a ball of spaghetti. And that is such a tedious thing that there's actually a whole technology just for doing that. Dependency injection, right? Dependency injection is like the spaghetti making technology, right? You take this strand and weave it in there, and this strand and weave it in there, and this strand and weave it in there. Orchestration in an async process, and this is something that I don't think is necessarily spelled out in the docs anywhere, but you don't write subsystems that internally construct channels. The constructor argument for any subsystem is typically a list of channels. And that means that the person who's assembling subsystems gets to choose what the policies of channels are and how the channels are going to be used. Error handling, in a non-async world, we have objects, they might throw exceptions. In the async world, you learn to write subsystems that will behave independently of anything that's a channel away. Right? They need to cope with their own errors, period. Right? They got to deal with their own crap. They don't throw exceptions. And now that can include, I die. Right? One way of dealing with your own crap is saying I die and have a supervisor layer that comes in and does something. But all these things, they don't know and they don't care what the other systems are doing. They do not presume what's going to happen on the other side of the channel. The only way they can see something on the other side of the channel is data appearing on the channel. Right? They're not going to see, this thing over here blew up. They're going to see data on the channel, or maybe they're not going to see data on the channel because the thing blew up, but they're not going to see things blow up. And then finally, and this one's really important, is how do you model state in this world? Well, if you go back and look at the examples that I showed earlier, they were actually purely functional. Stateful behavior emerged by having a loop where you could put things in and then put things out on channels, but the loop itself, the internal state, we were recurring over values. So that was purely functional. That is, in fact, really great. And that's something that you could do in any language, pulling stuff off a queue. You could take a functional approach and do that. But in Clojure, we have another choice. You can use all of Clojure's other concurrency primitives, what I call the unified succession model. And this is a whole other talk in itself, so I'm not going to go there entirely right now. But Clojure's atoms, Clojure's agents, Clojure's reference types, all those types you can use in conjunction with this. So you can have communicating sequential processes that only work with functional values, or you can use these other state primitives. So one of the things that this immediately takes you to is that in order to do all this, in particular the orchestration and the error handling, we can't just have those simple coordination channels that I talked about before. There has to be an ability to put buffers on channels. And so there's a set of very straightforward semantics. The basic coordination primitive is channel, which is unbuffered, which means that a producer and a consumer have to rendezvous to exchange a value. It's a coordination point. You can also have a fixed channel, which blocks when it's full. So that's just a channel that takes a number as an argument. Or you can have a sliding channel that drops old stuff when it's full. Right? So I'm going to drop anything that's old. I'm just, I don't care. I can't keep up, so I'm just going to forget about it. Or you can have a channel that drops, a buffer that drops the newest one full. And you could extend the system to do other things besides this if you want, but typically you're not going to. You're not going to need a lot more than that. This implies, well, it doesn't imply. We benefit greatly at Cognitect from having a visual vocabulary for doing architecture diagrams that's in terms of this. And I took one of them and I just stripped out all the text. So you could just see the basic vocabulary. And so what you're seeing here is that the little things that look like squished home plates are channels. And notice that the box represents a subsystem. So the whole box at the top is a subsystem. And this subsystem communicates with the outside world through no interfaces. Right? There are no interfaces. The only way it communicates with the outside world is through 4 channels. And if you go and look at where the arrows are pointing, it appears to consume from 2 channels and write to 2 other channels. The insides of this thing are more complicated in some cases than a single process. So in this particular one, there's a single-threaded process, that's the one inside the little thread there, talking to another single-threaded process directly. Right? So doing something lower level than what we're talking about here, like having 2 things that are intimately coupled, one thing directly calling into another. And then the other important piece here is the little tiny box with a dot pointing to a table. That represents, if there was just a table there on one of our architecture diagrams, that would represent a piece of immutable state, something that was being recurred over in this. But the fact that there's that little tiny pointer pointing into it means that that's a closure atom, that this is a reference to state that could be aliased somewhere else. It's still thread safe, but it could be aliased somewhere else. Other people could see it. Other people could observe its value. Forcing ourselves to draw these diagrams of all the... If we're going to make anything that has machinery that's not purely functional, it has one of these pictures. We have thousands. We also take an immutable approach to making the pictures, which is unfortunately not... We use OmniGraffle primarily. We take an immutable approach to making the pictures, which is if you ever make a picture and you decide you don't like it, and you want to make a change to it, the first thing you do is duplicate it. So all the old pictures, OmniGraffle, I wish there was a way in OmniGraffle to, maybe there is, I should look, some way to lock things, because every once in a while I forget and I commit mutation, which really makes me sad, because we have this archival history of all the things that we've made. And this is incredibly powerful, and it's really different than programming OO style with interfaces. It's also really different than programming with actors. So there's a nice book, 7 Concurrency Models in 7 Weeks, that Paul Butcher wrote. And actually, Paul, I've not met him, but I reviewed the book, and he's speaking here, I think, during this time slot. So you should tweet that you feel like you got the best value, because I'm going to talk about his stuff too, or a little bit right now. But I'm actually looking forward to meeting him. I have to go and find him during the break. And so he gave several examples of actors, and I have ported those examples to use core.async. And I can point you to those slides. But the actual point I want to make is that I can't straightforwardly implement the architecture picture I just made with actors. Right? So this is important. In the Clojure community, we're not fans of actors, and this picture is my best current attempt to start to explain why. So actors couple a mailbox with an object. Right? Those 2 things are directly connected in the actor model, which means that you can't make this picture. Right? I can't have N channels consumed by one process. There's a one-to-one association. There's no, right? Actor is the most primitive thing. There's not something under actor that's like, here's the mailbox and here's the thing that processes it. So when I draw this architecture diagram and I sit down to do it with actors, I'm like, I don't know how to do it. The actor model doesn't say anything about how to do state inside an actor, and typically it's up to your own recognizance for that. So there's 2 things that typically happen. One is that it's purely functional, which is good and recommended. So it's just the kind of recur idiom that I showed. The other one is you do whatever you're used to doing in your language. And so you'll see people reasoning about what happens when I use an actor and then I make a mutable thing inside my actor and I let other people get access to it. It's like, yucky. So with Clojure, I can use the unified succession model inside. I cannot make a direct connection between 2 processes with the actor model. Right? If 2 processes are going to talk, what do they have to do? They have to go through a mailbox. right? This guy has to put something in. And that's a great abstraction. It's not like that's a bad idea, but it's not always the thing I want. And then finally, having this level of decomposition that's one level more granular than actors makes it a lot easier, in my view, to write systems that are testable. Because now I can do my testing without actually using the mailbox semantics of actors. Right? I can test the internal loop as a pure function. Or I can test the internal loop without using that plumbing. Or I can use a different version of that plumbing. Right? I can create channels with policies that I want for production, for my production system, but I can create channels that have some other set of policies to help me facilitate testing this code. And I think it's pretty obvious that queues and processes are more primitive than actors. Right? Actors are a merger of those two things. Now, in fairness to the actor model, I think a place where it really starts to add a ton of value is when you want to have unified semantics in process and out of process. Right? That's where things start to get exciting with the actor model, because this is a model, right? This model doesn't run out of process. Right? It has things in it like me dynamically deciding which mailbox to connect to. Well, if I'm not in the same mailbox as a process, I can't make that decision. So actors' limitations are partially about wanting to have a unified model for in-process and out-of-process operation. That's not an objective of core.async. I'll come back. So, what else do I want to? So the last thing I want to look at, just as sort of visual fun, is talk about a couple of examples of people putting the JavaScript side of this to real-world use. So one of the most exciting libraries on the browser side ecosystem right now is a library called Ohm that David Nolan also wrote. And what Ohm does is it provides a value add layer with ClojureScript on top of Facebook's React. And I've linked here 3 really cool demos that, well, they're not really demos, they're really the real thing. And we will see if our web access will let us actually see one of these while we're in here. So let's go to Goya. So this is a pixel editor that's written with ClojureScript plus Ohm plus core.async. So you can play around and fill in things with the eyedropper. And I actually haven't used this much. And create projects and save PNGs. And the thing about this, there are a bunch of examples that are listed on the Ohm website, but I went through and pulled these 3 out because their source code ships on GitHub. So you can go and look at what it would take to build this with ClojureScript and core.async and Go. And the other one is that I actually have never played Android Netrunner, but there's a full implementation of Android Netrunner that all runs in your browser. That's all written with ClojureScript and React and core.async on the front end. So this is a pretty substantial application, and all the source code is on GitHub. So you can check this out. If I actually knew how to play, we could go and build some cards and whatever. So, and then just a couple of other things to mention. Communicating sequential processes, the underlying idea behind core.async, is realized in the Go programming language. So if you like this idea, but you don't want to be on the JVM or in the browser or don't want to be on Clojure, you could use Go. The other thing you could use is there's a Java library that does this. It's that cs.kent.ac.uk. JCSP is Java Communicating Sequential Processes. That also ships with a slide deck that is a scathing critique of object-oriented programming and a motivation for Java. And that might be something you wanted to share with coworkers who might find the Clojure stuff that I'm talking about a little bit too far-fetched, because it's all in good old-fashioned Java, so something that people would recognize. And with that, I would like to open it up and take a few questions. Dave Thomas. You can walk up to the mic, or I can just repeat your question, whichever is easiest for you.
Never turned down a microphone.
Rutrow.
So have you sufficient experience now doing this to know where to put the breakpoints when you're creating your quote, architectures of machines? Like, for example, will you still do functions, or do you try to make everything channel to channel or machine to machine communication?
Dave's question was not loud enough to be picked up, so he got to use the mic, but I'll repeat it anyway. How much experience does it take to know where to put the boundaries? I think it takes pretty sensitive design sensibilities to do this, but that doesn't really change regardless of what technology you're using, right? Figuring out where to put boundaries in systems is one of the key essences of what we do. But there was definitely a point, a couple of months ago where I just got overly enthusiastic, and I was putting in, channels everywhere. And Rich had done a diagram in Graphel that had like 5 channels in it, and I was going to implement the thing. And while I was implementing it, we always update the diagrams as we go. And I had added like 6 more channels. And his comment was, "You're writing Erlang now, right? You've gone too far." So the thing is that the channels, when they're used like a little conveyor belt, which is the use I've talked about here, there are some other more advanced uses that we didn't get into, but when they're being used that way, they need to represent an enduring relationship. They need to represent an actual conveyance, an actual, a step in between. And if you find yourself using them just to make asynchrony happen, or then you've overshot. But I think those sensibilities, one of the nice things about having these large examples is getting the ability to sort of work on that. The other thing is that the slide that I showed, let me go back to this picture. The slide that I showed, this is really advanced, right? I'm showing a system where I've chosen to wire 2 processes directly together without a channel in between. That's really unusual. I've shown something that's complicated enough that I want to have an atom to keep its state so that I can alias that state and access it elsewhere. That's not something you necessarily go to immediately. The one thing about this that you probably do fairly early is listen on more than one channel. And you've seen a canonical example of that in the lifecycle and work channel. Right? I have a channel that tells me when the show's over, and I have a different channel that shows me the work that I want to do. But this is really quite advanced. If you look at those 10 examples, and then the way that Go blocks are being used in the Netrunner app, or in the or in Goya, in that pixel art app, what you'll see is really much more vanilla usage than some of the stuff that I've shown here, and it's really that straightforward. Go, blah 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 blah, and it's easy to see. The other thing I would say is that if your logic is tortured when you're doing it this way, you did it wrong. Right? So we're continually surprised, and this is true supporting people using Clojure and specifically using async, at how people will paint themselves into a terrible corner before they realize they're in trouble. And then they post a code snippet, and you're like, I can't even start with this. It's so complicated, right? If it looks complicated, you did it wrong. So, and sometimes it means we did it wrong. Sometimes it means the feature doesn't exist, or there's something that's missing. But if you feel like it's complicated, I think you should get on the Clojure mailing list and say, I'm trying to do this, and it feels complicated. And a lot of times what will happen is, it turns out that's not the right abstraction for the job. The classic example of that from early in Clojure's history was software transactional memory sounded cool, and it had a big academic pedigree. And so everybody ran off and used software transactional memory for everything in their Clojure applications. I've been writing nothing but Clojure for my day job since 2009, and I've never used software transactional memory in production, not once. And that doesn't mean it's crap. It just means that it's suitable for some problems and not suitable for others. But that kind of guidance is definitely subtle and takes time. And this is about building machines. It's about state. State's hard. There's a reason that Clojure is mostly functional, and that this is out on the edge of it. That being said, we have to build I/O. We have to build user interfaces. So that's hard, and we have to deal with it. Question.
How often do you have to worry about the performance? How often do you have to worry about the performance of the channels?
How often do you have to worry about the performance of the channels? So David Nolan has done some benchmarking on the channels in JavaScript. Obviously, that's a place where you're probably more worried because Go blocks are complicated, hairy beasts compared to threads. We think about the 2 different process mechanisms, and easily making tens of thousands of Go blocks is not a big deal. So always there's an order of magnitude that matters. 10 billion Go blocks probably doesn't fit in memory on anything you're trying to run on. But you can take a fairly, I'll solve that problem if I see it attitude at the beginning, because you really can. Go blocks are quite inexpensive. And of course, threads are expensive. You know how expensive they are. So if you choose to use threads. So for example, in the project I'm working on right now, it has a lot of characteristics in common with Datomic's update system. And so I have chosen to model all of those. I actually really want those processes to be super first class. I want them to dump information into the log that says what thread they were and all that kind of thing. And there's a very small fixed number of them, so they're all done with threads. So there's definitely, right, this doesn't get you out of understanding how to build concurrent systems. It provides some powerful tools for doing it. Those tools are more effective if you know your way around those things. It's also the case that for basic stuff, there's less ways to shoot yourself in the foot. I mean, certainly, the most idiomatic usage is purely functional, right? You have something that's responding to a channel over a loop, and that's all you do. And those are, straightforward as you see in the examples. What are we looking at time-wise? Let's see here. I can't see the time at all. We'll keep going.
Can you give me more detail on error handling? What happens when one of those little square eyeballs throws an exception? Because in my experience, what happens is the program hangs forever.
So Jessica wants to know, what happens when errors happen in your program. It is I'll find a positive way to state this. It is the Clojure way to prioritize implementation for correct programs. The flip side of that is, Clojure is not the most helpful environment in the world telling you what's wrong with your program. And this is a fundamentally hard thing, especially when you're using Go blocks. Right? When you're using Go blocks, you're not on a thread that you control. You're being scheduled by this machine, and you're fundamentally async. Like, your failure is not necessarily where the cause was. It's not even on the same thread. And that's always more challenging. There's probably a whole talk to be had about that. But the thing that I would say that would help people most getting started is think smaller. And this gets back to people painting themselves into a corner and then coming on the mailing list with a 100-line program and saying, why doesn't this work? And my first question would always be, did you build it up one line at a time from programs that did work? And the answer is always no. And it's really go back to that. And part of this, I think, and I've made this argument before, part of this is that your first programming language defines your sensibilities for what is a unit of work. And so if your first programming language is Java, you think you should write 15 lines of code and then go check and see if it works. Right? Well, 15 lines of Clojure can be a huge program. Right? You definitely should not write 15 lines of Clojure and go see if it works. I mean, I write Clojure one S expression at a time, and I make sure those expressions work. And when you do that, you get yourself into that situation a lot less often. I'm not saying it wouldn't be better to have better error handling. I think the bigger thing, and that matters for correct programs too, is having more diagnostics of just what's going on. Right? How full are the buffers? How's the scheduling happen? And so that's something that is definitely an area for future improvement in async. All right, one more question.
What do you do about resource handling if you've got a source that's reading from a file, or say two sources, and then at the other end, a derived channel, there's something that's using that information, and then it's done, and there's nothing else that's interested in that? How do you make sure those file handles get closed at that point instead of at the end of the execution?
So the question is, how do I make sure that resources get cleaned up? When you can, scope that kind of resource use inside a single Go block, right? So Go blocks will have try-finallys in them, just like anything else. When you can't, and it's pretty unusual, right? I mean, that's another example of you're painting yourself into a bad place. If you create some asynchronous thing over here that makes a resource, and something over here has to be responsible for cleaning up, but you end up having to convey that information and saying, I'm going to go from point A to point B and make that work. All right, what time do we have in the back?
12:24.
Excellent. We'll go for one more minute. I'll say thank you very much. This is my first time at Philly ETE. I'm giving a talk after lunch that won't have any Clojure syntax in it at all. So if you like what I had to say and were scared of the parentheses, come back for that talk. Otherwise, enjoy your lunch. I will stick around at the front of the room and take questions if people have them. Thank you.